Yeah, my name is Austin Zinzer. I'm a geologist, been working on the Stibnite Gold Project for a number of years. I've been working closely with some of our consultants on the geochemical characterization program, and I'm going to be discussing those aspects of water quality today.
Thanks, Austin. How about you, Dale?
Hi, everybody. I'm having some internet issues today, so I had to come to this meeting as Austin Zinzer #2. But this is, in fact, Dale Kerner. I'm the permitting manager with Midas Gold. I'll be doing a brief introduction to the technical presentation today, just to kind of bring everybody into the now of where we're at and what we're going to discuss and the questions that we'd like to address and answer for you today. So thanks for joining us.
Thank you, Dale. And how about you, Doug?
Hi, I'm Doug Durbin. I don't think I'm having internet issues. I'm having a bad hair day again, as always. But I'm a chief scientist with Brown and Caldwell and have been working for about 4 years now, supporting Gold on surface water quality issues and looking at getting a permit from the state of Idaho for future discharges associated with the project.
Wonderful. Thank you so much, Doug. And just a recap for our webinars, you are always welcome to submit some questions into our webinar platform. If you have any, just go down to the bottom of your screen, click on the Q&A box, and it should pop up and you can ask any questions that you have. We will do our best to get to all of those questions with time allotting. And any that we don't get to, we will also do our best to get to you after the webinar is over. So Austin 2/Dale, would you like to get started?
Sure. Are you seeing the screen?
We are.
Okay. All right. Again, thank you everybody for joining us today. We'd originally provided this webinar back in September when the draft EIS was out. So there have been some developments in the project since that time. But today we're going to not go back in time, but we're gonna speak a little bit more conceptually about water quality at the site and water management and water treatment. We're not going to delve into some of the more recent project developments because irrespective of those, our approach to water quality characterization and determining an appropriate water management and water treatment approach still remains the same. Those principles remain the same. So, today we'll be addressing those issues. And to my mind, these are the questions that I'd like to address, or I'd like Austin and Doug to address over the course of the presentation today. And I think these are questions that a lot of people have, and that's why we've included them on the front end here. What is the existing water quality at Stibnite? Austin is going to go over in the first part of this presentation today, discussions about existing water quality out at the site and the causes of that water quality, both man-made sources and natural sources. There's a lot of mineralization out at the site, and that does impact surface and groundwater quality. Austin will also speak to how the proposed Stibnite Gold Project might impact water quality. There's been a lot of testing and characterization done to determine, what the materials that we're moving around and, how those might impact surface and groundwater quality. Then in the second phase of the presentation today, Doug Durbin will speak to how we plan to mitigate those impacts. How are we going to address those potential impacts to surface and water quality, both existing and proposed, again, because there is, very definitely existing water quality issues out at the site. So Doug will speak to, how we plan to manage, water as it's moving around the site during various phases of the Stibnite Gold Project. We'll have some good illustrations to demonstrate those concepts. And then we'll speak a little bit to the net benefits of the Stibnite Gold Project. Again, some of these data are still being worked on and being updated. But we very definitely have some goals with regard to improving water quality at Stibnite. So I've spoken a little bit to this, but I'll just buzz through these agenda items. I'm just going to do a very brief intro, and then Austin will talk about baseline surface and groundwater quality. and then speak to the geochemical characterization, how we've prepared or gathered data for these predictive models that estimate what our what water quality may be during various phases of the Stibnite Gold Project, and how we've come to those conclusions. And we'll also speak about water management objectives. This will get into Doug's portion of the presentation. And we very definitely want to protect and improve water quality during all phases of the mine and when the in post closure. So there's various topics that Doug will speak to about water treatment. How did we arrive at the proposed water treatment approach that we've included in the or that is included in the draft EIS? And again, this is a concept, a water treatment and a water management concept that is applicable to all alternatives. You'll note that in the draft EIS, water treatment is associated with alternative 2, the mod pro, the refined pro. But again, those concepts are applicable to all alternatives that are in the draft EIS, although they were not applied in that document, but they do have the potential to be. So Doug will dive down into some of those details again about how we've arrived at appropriate treatment technologies and how those will be implemented over the life of the project. So I think most folks on the call have probably gotten or have hopefully been to one of our presentations or more than one potentially on the Stibnite Gold Project. But just to recap very briefly here, the Stibnite Gold Project is located or will be located in Stibnite, which is east of Yellow Pine in central Idaho. It's a fairly remote site, pretty hard to get to, but that did not prevent them from mining the site for over 100 years. It's been the location of a lot of activity, and again, there's still a sizable resource there that is the target of the Stibnite Gold Project. So that's our general location. And the initial plan of operations, or the plan of restoration and operations, because it has so many components of reclamation and ecological restoration, hence the name, was submitted back in September of 2016. As you may recall, there was a modification of the proposed action that was submitted in May of 2019, the Mod Pro, and that was included in the draft EIS as alternative 2. The Pro was also included as alternative 1, but the Mod Pro was very much a refinement to the Pro, reduced environmental impacts, etc. But what we did want to maintain with that Mod Pro, even though it was a refinement of the Pro, is we wanted to maintain all of the restoration objectives that were included in the original Pro, including restoring salmon migration into the upper east fork of the south fork of the Salmon River. You'll see the blockage in the photo on the cover of the Pro here, the Yellow Pine Pit Lake and the cascade coming into its upgradient edge, which has served as a blockage to anadromous fish passage since 1938. And of course, there's also socioeconomic benefits to the Stibnite Gold Project. A lot of jobs for Idahoans, and one of the mineral resources at Stibnite is antimony, the namesake of Stibnite, the mineral that contains antimony. It is a critical mineral, one that we're very import reliant on. So this would be the only domestically mined source of antimony in the United States. And here's our calendar, which starts in the upper left and continues clockwise around. A lot of these steps have been completed. This upper tier of this chart has been completed. The draft EIS being released in August of 2020 with a 75-day comment period. You'll see our little balloon. We are here in the response to comment period. The Forest Service and Stantec are going through the many comments that were submitted on the draft EIS and preparing responses. And in concert with that, they're preparing the final EIS and the draft ROD, which we anticipate will be available later on this year, and potentially a final ROD toward the end of 2021. So this is kind of our big picture calendar of where we're at. So with that, we're going to transition here to Austin and his discussion about water quality. So Austin, number one, take it away.
Thanks for that lead in, Dale. That's a good overview. Yeah, so I'm going to be talking today about water quality and geochemistry and geochemical characterization, as well as existing water quality on site and some of the things that are influencing that, including naturally occurring mineralization and legacy mining activities. We have a slide here to get us kicked off. Acid rock drainage. Acid rock drainage is a big issue of concern for a lot of hard rock mining projects, and this is associated with dissolution of sulfide minerals, which create acid, and these things tend to accelerate the release of metals into surface and groundwaters. Now, we don't really think that this is going to be an issue at Stibnite, and I'll be presenting some data that speaks to that a little bit later on. And a key takeaway here is that even after almost 100 years of mining activities on site, there's really very little evidence for acid rock drainage occurring on the site. So in terms of water quality today on site, Midas has an extensive baseline groundwater and surface water monitoring program that's been going on since 2011. Consists of a suite of over 40 surface sites and 30 groundwater wells, which were initially sampled monthly and have been subsequently sampled quarterly for a number of years. This gives us a really good understanding of sort of existing conditions for water quality on site and how these things change in relation to some of the naturally mineralized areas and also some of the legacy mining features on site. I think some of the key takeaways regarding existing water quality on site are that arsenic and antimony are really the key metals of concern on the Stibnite mining district. We see these elevated in numerous locations throughout the mining site, often associated with unconstrained legacy tailings, added seeps, and other legacy mining features. And just again, there really hasn't very much evidence for acid generation processes occurring. So on the right here, there's a map showing just some of the various legacy mining features that are on site. They're coded as red and green based on whether they're going to be addressed in the pro and the mod pro mine plan. But I just wanted to point out some examples of these. We have historical adits such as the Defense Minerals Exploration Tunnel, which there's a picture of this on the left, and there's seepage from that adit, which is potentially impacting surface water quality. And then there's also, if we can go to the next slide, please. There's also sort of other larger features such as, this is a photo of the historical Bradley tailings, which were unconstrained mill tailings placed in Upper Meadow Creek Valley, which were subsequently covered with spent heap leach ore from 1970s and 1980s gold mining operations. You can see that material being covered in the historical photo. This is the large green area on the map. Sorry, I have a cat. But this is just an example of some of the larger legacy mining features that are known to impact surface water quality on the site. So on the right here, we have a map, and this is sort of color coded by median arsenic concentration in the stream, just to give a sort of general sense of how water quality changes as you go from upstream, such as in Meadow Creek, which is pictured in the lower left-hand corner. As the Meadow Creek flows past some of the soda material and the former Bradley mill and smelter site and the Hecla heap leach pad, we do see increases in arsenic and antimony and other constituents of concern in the river. Moving farther to the north, where Meadow Creek joins the East Fork, South Fork, the Salmon River. The Salmon River flows through the Yellow Pine Pit, which is pictured in the upper left-hand corner. That is a historical open pit mine left from 1940s mining operations. And then down to the confluence with Sugar Creek as the river flows to the north and leaves the Stibnite mining district. But we're going to be looking at some graphs showing water quality of key constituents as the river flows past these legacy features. Next slide, please. So on this graph, this is showing some of the major confluences with the various streams on site and some of the other features on site, such as the Yellow Pine Pit. This first graph is showing arsenic concentrations, and we can see that the median arsenic concentration, as shown by the green line, initiates actually off the graph below where it is now, but as it moves past the Soda and the Bradley Tailings Facility and the confluence of the Meadow Creek and the East Fork, we can see that water quality, arsenic concentrations steadily increase and increase especially so through the reach with the Yellow Pine Pit. And then decrease again at the confluence of Sugar Creek, where Sugar Creek, which has lower concentrations, actually dilutes the concentrations in the East Fork, South Fork. And throughout the entire area shown on the plot, arsenic concentrations are above the Idaho human health criteria for drinking water. There we go. Similar overall plot for antimony. We can see that higher up in the drainage, median concentrations are below the human health criteria, but they rapidly increase to exceed that as the Meadow Creek flows past some of the historical mining piles in Meadow Creek and increase steadily downstream until the confluence with Sugar Creek in the East Fork. Next plot shows mercury concentrations. So these behave somewhat differently. Mercury generally remains below the chronic criteria for aquatic life throughout the area of the Stibnite mining district, but does increase during some periods with the below the confluence with Sugar Creek, and that's due to Sugar Creek draining the historical Cinnabar Mercury mining district and introducing that constituent into the surface water. So I've talked about some of the legacy mining features and how those impact surface water quality. But another key component of the picture here is that there's a lot of naturally occurring mineralization in the Stibnite mining district. Of course, we have the three known mineral deposits which are targeted in the Stibnite Gold Project, but there's also a lot of other areas of elevated arsenic and antimony occurring in the district, and that's sort of displayed on this map, which is derived from well, it's showing soil and rock samples, as well as silt samples collected for exploration purposes, and they're color-coded by arsenic concentrations. And you can see that the elevated arsenic occurs throughout a large portion of the Stibnite mining district, primarily on the east side of the Meadow Creek Fault, which runs right through the Hanger Flats and Yellow Pine deposits. So water concentrations draining mineralized areas are naturally elevated in metals. And this slide is showing some information from a characterization study prepared for IDAQ back in the 2000s, which estimated what natural background conditions are in groundwater and did seepage from mineralized areas. And you can see that arsenic is for the most part consistently elevated above the human health criteria, and antimony is elevated in seepage from mineralized areas. So both legacy mining features and naturally occurring mineralization are leading to degraded water quality in the Stibnite mining district. So I'm going to switch gears here and talk a little bit about the geochemical characterization program and some of the work that's been done to support predictive modeling of what water quality might look like due to mining activities. So the geochemical characterization study was, this is work being done by SRK Consulting out of Reno. And I've been working with them for a number of years to on sample selection and making sure that samples are representative of all of the different types of geological materials that we have on site. So some of the sampling included samples of ore and development rock, as well as legacy mining wastes, material that's going to be representative of the mill process material, and then also additional samples as needed. But the general characterization consisted of multi-element geochemical characterization to know, what constituents are in our geological materials, and then some short-term leaching tests, acid-base accounting to figure out if the samples are potentially going to generate acid rock drainage or not, and also humidity cell testing, which looks at sort of long-term dissolution rates and long-term release rates. And we have a picture of the humidity cells, so it's also on this slide. But so this plot here, this is showing effluent pH from our humidity cells over a course of number of weeks. And these, you can see that we ran these tests out, a lot of them passed 140 weeks. So this is a very long time. And basically weekly, these cells are exposed to alternating cycles of moist and dry air in order to mimic and accelerate natural weathering processes that we might expect if these materials were mined and placed in development rock storage facilities. But the take-home rate point from this plot is that the pH has remained circumneutral throughout the duration of the tests in all cells. And this is consistent with the behavior of legacy mining wastes on site and sort of natural observations of what's going on with materials that were mined almost 60 or 100 years ago. This is some of the information from the acid-base accounting study, and this plot is showing neutralization potential ratio versus net neutralization potential. But what you need to keep in mind here is that all of the samples falling in the green box are not expected to be acid generating because they have ample neutralization capacity. And this is from the presence of carbonate minerals such as calcite, dolomite, and other carbonate bearing phases in the rocks of the Stibnite gold deposits. And these carbonate minerals are both occurring due to primarily as presence of limestone units and other carbonate bearing rocks, but also due to hydrothermal processes resulting in formation of carbonate veins in a lot of the altered materials of the Stibnite Gold Project mineralized zones. The samples falling within the orange box on this plot are those that are potentially acid generating materials, or PAG. But if you look at the samples in there, most of them are red, and those are indicating that those are ore grade. And we do know that our ore grade samples, the material that's going to be processed through the mill, a lot of those do have higher sulfide contents and therefore have higher acid generation potential. But very few of our non-ore grade samples fall in that orange box, and we don't therefore anticipate any issues with acid rock drainage. That said, we do see release of arsenic and antimony at concentrations that exceed the drinking water standard. So this plot is showing, again, the humidity cell data with the weeks on the horizontal axis and some of the release rates in milligrams per liter for arsenic in this case on the vertical axis. You can see that many cells have released arsenic at concentrations that exceed the strictest potentially applicable water quality standard. So this is important information that we've taken into account as we move the project through various design phases and look at ways to reduce interaction of precipitation and other water with our development rock in the project. Great. So I think this is my last slide here, but this is basically just showing how the various pieces of the environmental modeling fit together. I was just talking about the geochemical data that is supporting the site-wide water chemistry model, which is in the purple box on the right-hand side. But other sources of information that feed into this model include the site-wide water balance, stream and pit temperature modeling, and also the hydrogeological model. And I think at this point, I'm going to hand it over to Doug, who's going to talk about management strategies.
Okay, thanks, Austin. Sorry about the delay there. Yeah, let's talk a little bit about water management and treatment, because this is the really comprehensive approach that we take to making sure that the water quality in the future is going to look better than the water quality associated with the site today. So we have been putting together and continue to put together a water quality management plan. It's a large, comprehensive document, multifaceted, takes into account engineering, surface water quality, treatment, storage, conveyance of water, and so literally tracking every drop of water that runs around the site through the construction phase, the operations phase, and the closure and reclamation phase. And the overarching goal, of course, is to be able to comply with the Clean Water Act. And we think we'll even go farther than that and improve the net water quality that's at the site today. That includes an approach to managing and then treating all of the mine impacted water that will be released back to the environment. And that treatment, like I said, extends through all the phases of the mining process. And the overall treatment program has been designed so that regardless of which of the EIS alternatives may be selected, the treatment process can be adapted to fit any of those. So it's not a one size fits one, but kind of an adaptive to be able to fit all as needed. Importantly, the water management plan has already been viewed as a draft by the US EPA and by the state of Idaho and other agencies, and they commented profusely, and we have addressed those comments in the ongoing draft that is still in development and forthcoming. Next. So the big picture objectives of water management would be to protect the surface and groundwater quality during operations, and of course during the construction phase before that, and reclamation afterwards. The big picture long term is to make sure that 50 years, 100 years from now, the water quality associated with the site will be demonstrably better than it is today. That's part of the commitment from the Pro. And then in addition to that, if we think just beyond water chemistry, there's also been a lot of work done to look at how to make sure that we don't have negative impacts on stream temperatures, because there are so many species that depend on particular temperature regimes, including some listed species. And so in addition to worrying about things like arsenic or antimony or mercury, we're looking at water temperature, a more physical parameter, and making sure that we're also taking care of that. As I said, it's a holistic or a comprehensive view. The three big picture pieces that we talk about are avoiding impacts whenever we can. And I'm not going to go through all the bullets there, but there are steps taken to make sure that we don't touch any water we don't need to touch, for example. And then minimizing impacts so that if we do have some intersect with water at a portion of the site, we try to make that as minimal as possible, as little change as possible from natural conditions. And then mitigate, which means that if we do have something that may cause a change in water quality, like having water that we're mining, pulling out of a mine pit, that we take care of that water. We either hold it and reuse it, or we treat it before we release it, but we somehow mitigate our effects on that water. And importantly, is that big blue cloud in the upper right-hand corner shows adaptive management is a key part of that. And that's a very important principle that means that as things go on, There will be changes or unexpected events. Some might be natural events. Others might be changes in a mine plan or a schedule. And we want to make sure that whatever we do to manage water is absolutely adapted through those changes in the future so that we always do a better job as time goes on rather than falling behind. So in terms of a sort of an overview, this is a generalized graphic, but a couple of the things that we do that are really important are to make sure that we keep the clean water clean. And so you can see some of these light blue lines that are running around the edge of a couple of things, especially over toward the left-hand side of this graphic. And one of the first things that happens when you begin construction on a mine like this is that you make sure you reroute the waterways that are otherwise would come in contact with your mine features. And so essentially you provide these reroutes or these diversion channels so that any water that's running from a clean part of the site or an untouched part of the site doesn't go all the way into the mine feature. It's intercepted by one of those channels and routed around it. So we keep the clean water clean. Another thing you can see on this graphic are some of the sort of darker blue or maybe turquoise ponds, and we have strategically located a series of ponds across the site, and that's where we will catch the water that does come in contact with mine materials so that we make sure it doesn't discharge into surface waters before it is either given a chance to be reused or, if necessary, that it would be treated to make sure it is clean enough to be discharged to surface waters. So rerouting water that we don't touch and then containing or managing water that we do touch are two of the biggest picture pieces of water management for us. Here's a sort of a zoom in. This is the tailing storage facility, and you can again see those run-on diversions so that water coming down the side of the hill doesn't make it all the way to the top of the tailing storage facility, and it is caught by a reroute, in some cases of an intermittent stream, and in some cases a perennial stream. Another feature here at the bottom is an underdrain. In some cases, we want to make sure that the water, the groundwater that was coming down through a valley or down a slope doesn't get intercepted by a feature. So instead, we basically create conveyances to move that groundwater from above the feature to below the feature without coming in contact with the feature. So in other words, moving clean water either around something or in some cases under something is a good way that we keep our clean water clean. So during construction, this is the earliest phase of the mine life, and during construction, we start to build all of those diversions. In addition to building the diversions, we are looking at some other activities that will improve water quality. Toward the middle of the feature there, you see soda removal, and then you see the pre-stripping of the Hecla heap. Those are activities that are going to be taking out legacy materials that currently are known to contribute arsenic and antimony and other things to the surface waters. So by removing those before mining ever starts, we actually have begun to do things that will improve water quality for the site overall. There's a section of Meadow Creek that has been rerouted at one point. That will be rerouted again to allow for a mining pit, but that next reroute will be permanent, and we'll have a lot of habitat components put in there because that stretch of the creek serves as good habitat area for several different fish species. Okay. The next phase is operations, and operations obviously is the mining portion of the mine life, and we continue to divert that clean water around the mine facilities, and we make sure that we are reusing as much water as possible for the water that we touch, the water that is either pumped out of a mine pit to keep it dry, or water that may come in contact with development rock, or maybe a storage pile of the ore. Water that's falling on the mine processing facility will be captured, and all of that will be stored and reused whenever possible. And in the event that there's excess water, then it can be treated and released. And then finally, during the reclamation phase, this is when things are being cleaned up and covered up so that the surfaces that might contaminate water are not coming in contact with the water. A big focus of this period is dewatering the tailing storage facility, and then that will have a cover put over the top of it. There will be the reestablishment of some of those streams. In other words, the diversions of most of the streams are not permanent. They're put back into a location that's more like their original geographic positioning. And then we also would be managing any inflows and outflows of open pits until they're either backfilled or otherwise decommissioned. All right, a key feature that I've talked about a couple of times of water management is treating the water. And this is what would be done before water is discharged back to surface waters for any of what we're calling the mine impacted water. The treatment plan has been put together, and again, it can be adaptively managed to fit any situation that may come along. The primary facet is to comply with the Clean Water Act, and that means meeting state water quality standards and seeking to avoid impacts to surface waters. So the discharges that would be made under that permit to be issued for this mine would make sure that no discharges would exceed the permit limits. That permit will be issued by the state of Idaho. It's called an IPDES permit. It'll have numeric limits for a number of parameters that I'll talk about in a minute. And our goal is to ensure that we never exceed those limits. The performance and effectiveness are demonstrated in the water treatment plan that's been put together. It's put together using engineering principles, and we know the concentrations and the volumes and the timing of the water. So we make sure that the treatment system that is in place is adequate to handle any water that comes at it from whichever source it may originate. The analysis of that water quality work was submitted in the draft EIS. There is supplemental information that's still being put together that will be reviewed for the development of the final EIS. And then, of course, all of that same information will be reviewed by Idaho DEQ as they consider the IPDES permit development. There are two different phases of treatment that we're really looking at. There is active treatment, which means the addition of chemicals and doing things inside tanks and sort of looking like a traditional wastewater treatment facility. And that will be used all through a portion of construction, all the way through operations, and even through a portion of closure. But then after closure, water quality will eventually improve because we're covering up all the areas that may have contaminating substances until the point where there would only be the need for what we call passive treatment. And passive treatment means you don't have buildings and tanks and pumps and motors and things like that. You're running water through a system that is still providing measurable treatment, but it's done in more of a natural manner, in this case using biochemical reactors, or some people call them wetlands. They're sort of a modified version of a wetland, but that passive treatment is able to be used long-term or as long as necessary on a site like this. And the goal is no degradation of existing water quality, certainly. And then the idea is that the whole process can be represented in terms of flow sheets and plans so that it can be evaluated from a technical perspective as opposed to just sort of a narrative. It will be shown in engineering detail that can be evaluated for its efficacy for the proposed use. As I said, the treatment system would be adaptable and scalable through the entire mine life. And an important thing to know is that the plan is not to discharge any of the actual industrial wastewater. And that by that, I mean any water that is part of the mine or processing loop, water that goes into the tailing storage facility or comes back out of it. That water would be in a closed loop such that none of it would need to be discharged at any time during the mine life. The only time water like that may need to be discharged is during closure of the tailing storage facility, when there will be water that accumulates at the surface of the tailings, and that could be slowly decanted off and treated for discharge as needed, although even that would be minimized under the plan that has been developed. One thing that's important to understand is there's a lot of seasonal variability out there. Most of the water is associated with the spring snowmelt, and so there's a big peak in stream flows. And most of the rest of the year, approximately 8 or 9 months of the year, there's actually minimal flow that comes through most of those smaller tributaries, and associated runoff is also very small. The storage ponds and the treatment plant are all interconnected. There's a whole spider web of pipes and pumps that link things together so that we can take advantage of storage potential in one area when we have little storage in another area, and we can move the water back and forth so that ideally we keep it until we need to use it for the treatment plant or the ore processing plant, and don't need to treat it and discharge it. During operations, there would be some residuals, some solids that would be generated through the treatment facility. There's adequate capacity for all of those solids to be stored in the tailing storage facility without causing any negative problems there. So that's nice to have that on-site disposal opportunity. And then during operations, we would be doing pilot studies of these passive treatment facilities to make sure that at the time of closure and reclamation, we have the right technology and the right scale of technology to supplement and then replace that active treatment with the passive treatment. We've gone through, and I'm not a chemical engineer or a industrial wastewater engineer, so I'm not going to explain each of these methods to you, but suffice to say that a series of different technologies, all of which are proven for some uses, have all been evaluated, and the treatment engineers have come up with those that are listed with a yes here as being a possible part of the overall treatment plan. You can see the second one there, iron coprecipitation, that is identified as our principal treatment process. It's good because it takes out a wide variety of metals. And then as needed, we might also be able to use evaporation just to reduce the volume of water that might have to be treated, and various other things like the sulfide or membrane treatment. And the last one on the list there, the biochemical reactor wetlands, that's the passive treatment technology that I talked about. So the overall, the process of developing the water treatment plan is that endless loop that you see there. The plan gets put together, you do some testing to see how it would work for your site at a bench scale or sort of a laboratory scale. You review the results, make any changes that you need to make, and then eventually you put together the pilot scale tests for on-site treatment and evaluate those, and finally design the actual plant and put it into operation. But this loop continues because you're constantly evaluating the ability of your treatment system to attain the permit limits and get the water as clean as it can. So I'm not going to go through all of these, but the ones that are highlighted here, arsenic, antimony, mercury, are the ones that Austin mentioned as being at elevated levels in at least some of the surface waters on site. But all of these parameters are expected to be considered in the IPDES permit development process, not because there's necessarily a concern about generating a lot of them, but some of these are very typically associated with mining. So we want to make sure that we look for anything that could be there. Others have particularly low concentrations in the Idaho water quality criteria, things like copper. It is of concern because its criteria recently changed. And so we'll be looking at a much broader swath of parameters in thinking about permit limits than just the ones that have already been identified as problematic on the site. And again, just an overview here, there are really two different treatment needs on the site. The primary one is associated with the water that will be at the mine itself, and we're calling that mine impacted water. That's what I've talked about so far in all of my comments today. Any water that needs to be released would be treated at a wastewater treatment facility and then discharged an outfall, likely on the East Fork, South Fork of the Salmon River, close to where the ore processing facility is. There may be a supplemental or additional outfall at a point on the lower portion of Meadow Creek. That would be in place to allow us to augment some flows in Meadow Creek, because as I said, that tends to be good habitat for several salmonids. And so it allows us to use this really high quality treated water as a habitat enhancement for some of the fish. That third bullet there is really important. The seasonal variability that I mentioned before extends to the discharge as well. And our current hydrology modeling indicates that during many years of the mine life, there would not be discharge for much of the year. In a few of the years, there wouldn't be discharge expected at all. For example, the first 2 or 3 years of mining, there wouldn't be enough water to exceed the demands of the plant. And so all the water that is touched by mining activities would be reused in other mining processes. So there would be no need to discharge that water. A couple of the years in the middle of the mine life, there would be more need for discharge. That's when we would probably be supplementing the flow in Meadow Creek. But it's generally seen as a good thing when you don't have to treat and discharge water constantly. And that appears to be the case for us based on the hydrology out there. The other treatment is almost a minor thing, and that is there will be a worker housing facility at the site that will produce a small and rather constant flow of water that's associated with the cleaning and showering and cooking and so forth that would go on at that facility. And so that would have its own treatment facility, a very conventional sort of off-the-shelf kind of treatment that's highly reliable. And that discharge would be to the upper East Fork, South Fork, just adjacent to the housing facility. As I recall, it would contribute something like 2% of the flow of the stream at that point. So in summary, we're going to comply with the Clean Water Act. We have put together the treatment technology with the best scientific and engineering practices that are available. We're focused on ensuring that that mine impacted water would only be discharged if it meets the permit limits, and if we can't find another use for it, and that we won't degrade the ambient conditions. It occupies the entire span from beginning of construction through post-closure, and the technologies that we're looking at are all proven at other sites, including other mine sites. So we're not inventing some new mousetrap here. We're using things that are known to work, and we make sure that we're able to adapt it to any of the alternatives or any evolution of the mine as the mine life goes on. I believe that's the end of my information. Now I think I'm going to throw it back to Austin here to talk about a new acronym that we have.
Yes. So just about 2 weeks ago, Midas Gold, the U.S. Forest Service, and the Environmental Protection Agency entered into an ASAOC, which is an Administrative Settlement Agreement and Order on Consent for Removal Actions. The acronym is much easier to say. But basically what this does is it directs Midas Gold to perform some cleanup of some of the legacy mining materials on site over the span of approximately 4 years. And then it also provides liability coverage should the project be permitted and move forward into construction and development. I was showing the map previously of some of the legacy mining features on site, which had both red and green areas, and the green ones are slated to be addressed in the Pro and Mod Pro. But all of the red areas, which are outside of the extents of Midas's plans, we really had no mechanism to address those legacy mining impacts without inheriting additional liability. So this ASAOC basically provides a means for Midas Gold to clean up the remaining legacy mining materials that are distributed throughout the Stibnite site without inheriting circular liability for this. And I guess, yep. We will be having a forthcoming webinar specifically on the ASAOC if there's additional information.
Wonderful. Thank you so much, Austin. As he mentioned, we will be having another webinar on February 11th that addresses the ASAOC. And I highly recommend that you guys pop on for that one as well to get some more information on that. We do have a few questions and we're going to open it up for other questions. Doug, the first one is for you. You mentioned that water quality is planned to be better in 100 years than it is currently, but could you elaborate on some periods in between, like 10 years, 25 years, 50 years?
Sure. The goal is to never have any degradation of what the water quality is today. And I think that the easiest way to picture that is that right now, the water quality exiting this site is affected by both the natural geology, which we know contributes some arsenic and antimony and And actually the mercury is mostly associated with another mine in a different valley over the hill. But that natural geology contributes some of those metals, and then the legacy mine materials certainly do as well. And one of the first things that will happen at the beginning of construction is that Midas Gold will start to pick up some of those legacy materials and move those into other places where they will be essentially more isolated from the environment. So things that are today contributing to water quality degradation will be moved. Austin just talked about the ASAOC, and phase one of that also talks about during construction, actually even before construction, possibly as early as in the next year or two, beginning to pick up some materials and move them away from areas where they can contribute to water quality degradation. So literally from before the first mining is ever begun, there will be actions that are intended and expected to improve water quality. Then all of the water that is contacted by Midas Gold during mining, and as I mentioned, that might be coming off of development rock or out of a mine pit. It may be dewatering water. It may run off of a roadway. It may run off of the ore processing facility. All of that water will be captured and mostly reused, but if necessary, it will be treated before it's released. And the treated concentrations of that water for things like arsenic and antimony will be much less than what's already in the stream. So any water that Midas Gold treats and discharges will essentially clean up the stream to some degree, because the treated water is cleaner than the ambient water. So between the removal of these legacy materials and the treatment of water, we have two different things that kind of right off the bat will help water quality. As the mining goes on, there are various things, including putting an impermeable liner under the tailing storage facility, putting covers onto portions of the development rock after the end of mine life, and putting soil covers over the tops of areas so that rainwater and snow doesn't contact things like development rock. All of those are intended to make sure that after the mining is finished, that the landscape itself is not left with the same degree of exposed material that is there today. So by making sure that we don't degrade water quality during operations, and that we reclaim the site to make sure that in the future, there won't be the opportunity for the same kinds of loadings that we see today, that means that whether you look at the first year of construction, the first year of mining, the first year of closure, or the 10th, 25th, 50th, 100th, or 500th year after reclamation, the goal is not to see water quality ever at the situation it is today. It is always expected to be somewhat better, and by the end of the mine life, it's expected to be measurably better than today's ambient conditions.
Excellent. Thank you, Doug. We did have another question on water cleanup. What types of methods are we looking at using for cleaning up water? He specifically asked for like osmosis, aerobic, anaerobic bacteria, active carbon, anything else.
And there was a slide that I had that listed the treatment processes there. Yeah, these are the ones that have been evaluated. Now, what this only talks about the industrial water. So this doesn't talk about the sanitary waste stream. The sanitary wastewater would be treated essentially through what they call a batch plant. It's a series of tanks and pumps that basically works in a small area, because we're not talking about a lot of water. But the iron co-precipitation is the primary treatment here. And in the event that there was a need to do any final polishing, then the sulfide precipitation can work. In some cases, membrane treatment may be used. There are some cases where, for example, you may have a water source that's located far away from where the main water treatment plant is. So you can bring in a mobile unit that would use membrane treatment to clean that water. So again, adaptive management means we have a series of technologies, and we can deploy them in either one location or a series of locations as sort of an as needed way to handle the water. But these are the technologies that have been evaluated.
Excellent. Thank you so much. And it looks like that's the last of our questions. So I'm going to go ahead and wrap it up for everybody today. As Austin mentioned, we do have our next webinar on the ASAOC. Our goal is to get a technical webinar available to you guys once a month, so that you can continue to learn about how the Stibnite Gold Project is moving along and get all of your questions answered. We will be doing periodical Stibnite Gold Project 101 webinars as well for folks that would just like to have a high level information on our project and where we're at. And we will continue to offer our office hours. Those will be virtual during the COVID times that we're all experiencing right now. And when it is safe, somewhere down in the future, we will look at opening those back up. But for right now, everything is going to stay virtual. And you can find all of that information on our website at midasgoldidaho.com/virtual events. So we hope to see you guys again soon. Thank you so much for spending an hour of your day with us. And we hope that you have a great rest of your day. Thanks, everybody.
Thank you.
Thank you very much.